Hello, everybody, and good morning. We're going to be talking about using kinematic equations again, something that we have done before. But now we're going to put a little twist on it. So you're going to kind of see here we have our normal kinematic equations for linear, also known as translational motion. And these can all be found on the equation sheet. These are the first three equations on the equation sheet that we have that will be given on test day. Remember, there is a couple little tweaks that we want to do. So uh, we usually write these. We don't put this whole, initial position right there. We say change in position is equal to all this. And then same thing right here, the change in position. Remember, we can more easily write this as delta x for displacement. Right? That's just an easier way to do it. And then there is one equation that can be used sometimes that is not actually included on the equation sheet, and that is that the displacement right here is equal to the average of your velocities times time. Okay, so these are things that we've done before. This is just for linear or translational motion. And now that we're dealing with things that are rotating, we actually, the physics doesn't change. Speed is still distance over time. Acceleration is velocity over time. All that good stuff. But now we're going to apply it to rotational motion. And so you can take these exact same equations and just switch out the variables for their angular variables. And we end up with something like this, right? So instead of velocity equals initial velocity plus acceleration times time, we end up with this. It's the exact same equation, but notice now we have angular velocity equals initial angular velocity plus angular acceleration times time. They are the exact same equation, just this describes something going straight, this describes something that is rotating. Okay, and so on and so forth for all of these. We can make these same little tweaks. We wouldn't put that, we would put change in angular displacement. We wouldn't put this right here. We could put just angular displacement, change in angle, right? And same thing for that one equation that's not included on the equation sheet. I would put change in angular displacement is equal to 1/2 angular velocity. This is the average of the angular velocities times time, right? So any of these equations are fair game, and they can be found. Let me scroll over here a little bit. If we go to our actual equation sheet right here, right, there's those first three translational equations that we were talking about. And if you scroll down to the bottom, we end up kind of towards the middle here, right underneath power. We end up with the rotational variance right there. Now, for whatever reason, they don't give us the third equation, but it's right there. You can easily just swap out those variables and you can get that same equation. All right, so same thing. It's fair game to be used. Just for whatever reason, they don't give it to us. Okay. Couple other little tips to remember is, these equations can always be used whenever there is a constant acceleration. So the force is staying the same. That's making the acceleration stay the same. And we call that uniformly accelerated motion, or UAM for short. Okay. So same thing, if we're talking about translational, we're talking about when something that's moving in a straight line has a constant acceleration. And now when we're talking about rotational motion, we're talking about when something is rotating. So it's speeding up or slowing down at a constant rate with how it's spinning or rotating. Okay. And other little just kind of tips that we want to remember when we're talking about something that is rotating in a circular fashion like so, right? Normally 0 is right here. This would be, just the straight 0 radians or 0 degrees. And when we talk about things that are rotating, we talk about them as they go counterclockwise, right? So something that is moving counterclockwise, CCW, counterclockwise for short, that is the positive direction. Just like you've done angles in math when things go up like that, right? That angle would be a positive angle. So that's going to be the positive direction. Anything that is going down opposite, going this way, right? That would be considered clockwise. And clockwise is the negative direction, right? So these are vectors. Just like everything else, vectors, the direction matters. So now we talk about counterclockwise and clockwise, positive and negative. So let's see these in action a little bit. You'll see the pattern. You'll see how these things play out, just like we used to do kinematic equations, and hopefully it'll make it seem, a little simpler. So here we go. All right, so first example here, we're going to read through it and mark it up as we go. A tire has a counterclockwise, so that right there tells me that's moving in the positive direction. Angular acceleration of 16 radians per second, and reaches a counterclockwise angular velocity of 95 radians per second over 0.25 seconds. So there's a time. This is a final angular velocity. All right, this right here is going to be our angular acceleration. So making our little list of values is a good place to start. So I know it's got an angular acceleration of 16. And it's asking us what was the initial angular velocity, right? So we are trying to find the initial angular velocity right there. So we can take a look at our equations. And we can look over at our equations and see which ones will actually work with the values we have. We do not have any displacements or anything, so it looks like it's going to be the very first equation that we can use. So we can set it up. Right, we're being asked to solve for initial velocity, so I'm going to rearrange this equation so it's equal to initial velocity. And once I have that solved for, or rearranged, now I'm going to plug in my values and get my answer. Okay, and then it just becomes a little plug and chug. 95 minus 4 right here gives me an initial angular velocity of positive 91 radians per second. Remember, that's positive, so that means that this would be moving in the counterclockwise direction. Cool? All right, moving on. Next up, we have a disk with an angle of 0. So that means that's its initial position. Rotates clockwise. So right there, clockwise tells me negative direction. And then that's an initial velocity. That's what it's rotating at times 0. And it has a counterclockwise. So that tells me a positive angular acceleration of right there for 2 seconds. So let's make our list, and it's asking us to find the final angular position. So it's asking me to solve for final theta right there. So let's make our list of what we know. And again, we can kind of look at the equations that we have to work with and figure out just from all of the values that we have, what equation can we work with. So it looks like we do not have final angular velocity. So the only equation that doesn't have final angular velocity is right there. So let's go ahead and plug everything in, and let's start with that equation. Right, once we have this, we're trying to solve for the displacement, like how much does it move. So I already have it solved for that, so now I just need to plug in my values and see what I get. Okay, a little plug and chug in the calculator. This is -50. This is 2 squared is 4, times a half is 2, 1. So -50 plus 1, this gives me a final angular displacement of -49 radians. Remember, we deal in radians when we talk about rotation. Right? So its final position, if it starts at 0 and it displaced -49, that would be its final position right there. Good to go. On the next one, all right, let's break it down. Carnival Ride starts at rest. That would be its initial angular velocity. And it's accelerated from an initial angle of 0, so that's its initial position, to a final angle of 6.3 radians. So that's its final angular position. By a counterclockwise, that tells me negative direction. Angular acceleration of, boom. What is the final angular velocity? So let's make our list. And you know what? This counterclockwise, I should know that's actually positive. That's not negative. That is a positive direction right there. And then that would be positive 2 radians per second squared. And we're trying to find what is the final angular velocity. Right? So we know the displacement. We know the acceleration. There's no time given in this. So if we look at the equations we have to use, we need to find the one that does not have any time given to us, which is going to be our third equation right here. Right? So now we just set that up and we rock and roll. Right? We already have it solved for omega, the final angular velocity, so we just need to square root both sides. Make your life a little easier. You know, this initial velocity right here is 0, so we can just make that 0. And now when you actually solve and you square root both sides, it's a little easier to deal with right there. So when we plug in our values, right, all of those things were positive, so we plug them in. So that's 2 times 2 is 4. That's a little over 25. I'd plug it into the calculator, and we can get a final answer of approximately, because it's a big decimal, 5.01. And this is an angular velocity in the positive direction, so that would be radians per second. All right, we're talking about rotation, so it's in radians per second. Cool. All right, last example. A wheel starts from rest. So it starts from rest. That would be its initial velocity at an angle of 0. Has a constant angular acceleration for 5 seconds. That's a time, so it doesn't actually tell us what the acceleration is. And it rotates to an angular position of -55. So that's the final position right there. What is the angular velocity after 5 seconds? So we are solving for the final angular velocity. So let's make our list of what we know. Okay, we don't know final angular velocity. That's what we're trying to solve for. And the one thing that is not given to us in any part of this problem is what the actual acceleration is. So when we're looking at our equations, we need to pick which equation can we use that does not have angular acceleration in any part of it. And so that would actually be this one right there. Okay, so we can set that equation up and then rearrange this equation. That should be, one of those should be a final. Oops. And then we can rearrange this equation to solve for the final angular velocity right there. So when we do that, make your life easy. This is the initial angular velocity was 0. Okay, and once we have this rearranged, right, so that we're solving for final angular velocity, just go ahead and plug and chug. So we get a final angular velocity of -22 radians per second. Remember, just a little thing to remember, this is negative, which tells us that this would be going clockwise, right? So it would be going with a velocity that is clockwise, angular velocity that's clockwise. All right. So you kind of see how each of these equations get used. Make your list of values. It makes things a lot easier to kind of pick up on and figure out which equation we're going to use. And get used to using that equation sheet. You know, you don't have to memorize these. The only ones that you need to actually remember how to do is these bottom two, right? Because they're not explicitly given to you on the formula sheet, right? These top two are, these bottom two, we got to actually, these, you know, the middle, the third one, you can kind of just figure out by changing the variables on the equation for the linear acceleration. This bottom one, we got to actually remember. All right. So good luck, and I will see you all tomorrow.